Hi class, welcome back to our third lecture on electrodynamics. And again, our main reference is Introduction to Electrodynamics by David J. Griffiths. If possible, I recommend, if possible, that you get a hold of this book. So to continue, we have studied about vectors last time, and now let's look at how vector transform in one frame to another frame. For example, a frame could be the three-dimensional, the way we used to look at three-dimensional coordinate system. And then how about if we tilt that three-dimensional system, or tilt the two-dimensional plane, for example. But before we do that, we look at the extended definition of a vector. A vector is a quantity, again, with magnitude and direction, but it also transforms with a change in the coordinate system. The coordinate system used to describe position in space is entirely arbitrary. It's not fixed. It's one's convenience to set a coordinate system. But for example, if another person, or if in another coordinate system you want to look at the vector, how would you transform that vector? Now, suppose x bar, y bar, z bar is a system that is rotated by an angle phi relative to xyz about the common x equals x bar axis. So here in this case you have this figure. The x-axis is the one that is towards you, the positive x-axis, and the negative x-axis is the one that's going away from you. And then you have the y-axis here and the z-axis here. And of course, since we tilt the x-axis by an angle phi, so we have here the tilted angle phi, and so the components of A will be changed in y bar and in z bar. So say for example in the original frame of reference, or in the original coordinate axis, your AZ would be this. This is your AZ, and this would be your AY. But for the new coordinates, your AZ would be this. This is now your AZ bar actually, and your AY would be this one. This is AY bar. That's your AY bar. So how would you do the transformation? So in this case you have originally your AY is equal to A cosine theta. This is the original angle between A and the original coordinate system. And then your AZ would be A sine theta. So you have your new coordinate system here, and the angle now here would be theta bar, and of course theta bar here is equal to theta minus phi. So your AY or AY bar or A bar Y would be just A cosine theta bar. And of course theta bar is theta minus phi, so you can expand this by the difference of two angles. So here you have cosine theta cosine phi plus sine theta sine phi, and then you will have your AY. If you simplify that, your AY would then become that one, and then your AZ will just be A sine theta bar, and then A sine theta minus phi, and that is of course your sine theta minus phi would be just this one. And then of course if you simplify that, this would be this one. So by the way, you have to use the idea that AY here, so in this case you have for A cosine theta would be AY, and then your A sine theta would be AZ. So that's why you have there. And of course you're already given that AX bar is already AX, because you are tilting on the x-axis, so the x-axis remains the same. So x is equal to x bar. So if you look into this, so if you just look into these two equations here, you can express them into a matrix notation. In this form. So this is just AY would just be equal to AY times cosine phi times AZ cosine phi, sine phi, and then you will have AY times negative sine phi, which is this one, and AZ times cosine phi. The blue one would just be here, and the red one would just be this one. So that's how you convert those two equations into matrix form. So in general, since you also have A bar x is equal to AX, then you can in general, your 3x3 matrix would be this one. A x bar a y bar a z bar equals 1 0 0 cosine phi sine sorry for that, 0 cosine phi sine phi, 0 negative sine phi cosine phi times ax ay az. That's actually the three-dimensional matrix that you can form with ax, ay, and az. This is just for the two-dimensional zy plane. So in general, if you rotate about an arbitrary axis in 3 dimension, the transformation takes the form this matrix here. So in that case, since x bar and x are equal, so your a bar x and ax would just be the same. So your rx here is equal to 1, rxy is equal to 0, and this is equal to 0. This is also equal to 0, and this is also equal to 0, and this one is cosine phi, this is sine phi, this is negative sine phi, and this is cosine phi. So that's how you transform a vector to, transform the vector from one frame to another frame, which is different from the original frame. So if you write that in summation, in a sigma notation, this is just that one. These are equivalent. So if you say I is equal to x, so if you say I is equal to x, then this would just be summation. So a x bar would just be equal to summation of j equals 1 to 3 r x j a j, but the j here runs from 1 to 3, and 1 to 3 would just be x y z, for example. So this is your ax equal to rx x ax plus rxy ay plus rxz az. But your rxy is equal to 0 and rxz is also equal to 0, like here is equal to 0, and this is also equal to 0 up here. So your ax would just be equal to, or your ax bar is equal to ax. And equivalently, you can also do that for ay bar and ayz. So in this case, you have this one. The one here represents the x, and the 2 represents the y, and the 3 represents the z. So if you look at that, your rxx is equal to 1 for, as I said earlier, and rxy is equal to 0, and rxz is equal to 0 as well. So formally, a vector is any set of three components that transforms in the same manner as a displacement when the coordinates are changed. But there's also a different kind of quantity. We call them tensor. These tensors are actually the generalization of a vector. For example, a vector is a quantity that is rank 1 tensor, and then when you have what we call a matrix, a quantity represented by a matrix, that is a second rank tensor that has 9 components. So this is these are the components, and the components are actually written this way. So that's how you write the second rank tensor. Or you can also if it's possible for 4 dimensions, then you can also write it for 4 dimensions. In this case, you only have 9 components. That is a 3 by 3 matrix. Because sometimes the vector can also be like 4 components. So you have that, and then you can write that more compactly in this manner. So when you want to solve yz, for example, then t bar yz, for example, this would be just summation of 1 k equal to 1 to 3, summation of k equal to 1 to L 1 to 3. This is just R Y K R J R Z L T K L. So since 1 means for k equals 1, that's x. So R Y X. So you have how many terms here? You have 9 terms, of course, here. So it's more than 9 terms, by the way. It's 27 terms in this case. So for a second rank tensor, you will have 9 components. But here you have to add like how many terms? There's so much terms there. In this case, you have 27 terms to add for this one. So in general, an nth rank tensor has n indices and 3 to the n components and transforms with n factors of r. By the way, a scalar is a tensor of rank 0, and of course a vector is a tensor of rank 1. So here you can see from here that this is a vector, and this one is like a tensor. A matrix is a rank 2 tensor. So now we will go to differential calculus. So much about vectors. So I know you will be able to transform a vector. You definitely have to practice on that, because that is very important as well as very necessary when you do advanced physics courses. So differential calculus, this is a tool that is used in electromagnetism, study of electrodynamics. So we start with ordinary derivatives. So if you have a function f of x, what does df over dx do, or the derivative of f with respect to x? What is that? So anyway, the derivative of f, so when you have a function and you want to get the derivative in basic calculus would just be df is just equal to f of x plus dx minus f of x. This is the df, the derivative of f. So if you get the derivative of x with respect to x, then you just divide this by dx. So in this case, if x is changed by an amount dx, then f changes by an amount df. So this is just the proportionality constant between the two. So sometimes a function is dependent on time, sometimes it's dependent on the position x, for example, or it's dependent on xyz, or it's dependent on xyz and time. So it could be a multi-variable function. So in that case, the rules would apply similarly. However, you'll be treating other variables as constant. If the case, in the case of a function that is, in the case that a function is a multi-variable function. So here in 17-A, in the function varies slowly with x, but in 17 in the 1.17b, the function increases rapidly with x. And of course here, the derivative gets larger as you move away from x is equal to 0. So here you have the derivative is the slope of the tangent lines of the graph of f versus x. So in this case, the slope is there, and here the slope is that way and the slope is that way. It doesn't drastically change, but here you have a slope that's in that orientation, and then you have a slope in this orientation, in this orientation, and then in this orientation. So if you go from this point to this point, the change in slope is very drastic. So you can see that the slope here is like that, and here is already like that. But here, the change in slope here is not that drastic compared to the other one. So gradient is just the same as derivative. Given a function of three variables, say for example the temperature T, which is a function of xyz. For example, in a room, you put an air conditioning system. So any point in the room would have different temperature, and the temperature would be dependent on the position. So if you're far away from the air conditioning system, then of course the temperature there would be higher compared to when you are very near to the air conditioning system. So in this case, when you find the derivative, it's not difficult. You just treat the other two variables to be constant. So in this case, you have the total derivative of a function that is dependent on three variables. So this one here, the derivative of t with respect to x, or this is called the partial derivative of t with respect to x, is the derivative of t treating y and z to be constant, and you just get the derivative of t with respect to x, and the total derivative would just be this one. So similarly here, you just get the derivative of t with respect to y, treat x and z to be constant, and here you treat x and y as constant. So in this case, you can actually write this into a dot product. A dot product, sorry for that. A product of two quantities with direction, because when you dot product this and this one, the x hat will cancel, and then this one, the x and the y hat and the y hat will cancel, and of course this one, the z hat and z hat will cancel. And this one, the total derivative of t, that is the sums of the partial derivatives with respect to x, y, and z, you will have this as, you can write this as del of t, which is this one, and dl here, which is this one. So this is dl. It's a vector quantity because it has direction, and of course, if you write that in your notebook, this is del with a vector notation above the del. That's del of t. Remember, when you dot two vectors, this is just ax bx plus ay by plus az bz. It doesn't have direction anymore. So this is your ax, this is your bx, this is your by, and this is your I mean, this is your AY and this is your BY, this is your AZ and this is your BZ. So it's just a repetition. So anyway, your del of t would be this one, and your dl is of course this one. And the del of t is actually the generalized derivative. This is also called gradient of t. So this is del of t is also called the gradient of t. Gradient of t. Or in symbols, that would just be that one. So this is the three-dimensional version of the ordinary derivative. So anyway, this is the geometrical interpretation of the gradient. So again, the gradient is the generalized derivative, and it has a magnitude and direction. So your dt, this is your total derivative, this is your gradient of t, and this is your, of course, dl that we saw before this slide. Now, if the magnitude of dl is fixed and searching around the various directions, varying theta here, the maximum change in t evidently occurs when theta is equal to 0. That is when cosine theta is equal to 1. When cosine 0 is equal to 1. So that's the maximum derivative. So for a fixed distance dl, dt is greatest when the motion is in the same direction as gradient of t. This is fixed. So dt is greatest when the motion is in the same direction as your gradient of t. So therefore, the gradient of t points in the direction of maximum increase of the function t, because the greatest value of the derivative occurs when theta is equal to 0. So when theta is equal to 0, both the gradient of t and the dl should have the same direction. And thus, the gradient of t points in the direction of maximum increase of the function t. Now, the magnitude of del of t gives the slope or rate of change along its maximal direction. So if you have like a mountain, that's then you can get the gradient of t. A mountain could be a three-dimensional summit. That's could represent a function. So here, if you look around, if you imagine, standing on a hillside and look around, and you find the direction of steepest ascent. So the steepest ascent would be the direction of the gradient. That is the direction of the gradient. So the slope, again, that's rise over run in two-dimensional plane, that's rise over run. But in general, that is the magnitude of the gradient, the slope. The direction of minimum descent is opposite to the direction of the maximum ascent. So of course, when you are in a hillside and you look up, that's the maximum ascent. And when you look down, that's also, of course, the descent. So when theta is equal to 90, the slope is 0. This means that the gradient is perpendicular to the contour lines. So it means nothing. So if you have a vanishing gradient, that is your del of t is equal to 0, then of course your total derivative would also be equal to 0. And this one is called a stationary point in the function t, x, y, z. So if delta t at some point is equal to 0, then that is a stationary point. And that stationary point could be a summit, like the top of the mountain, or a valley. That's also a minimum, by the way. The summit is a maximum, and a saddle point, or a pass, or a shoulder. So you have here a summit. So there, the gradient is 0 in this case. Or a valley, here you have also the slope is 0. And when you have a saddle point, it's also 0 there, the slope. So this is just a three-dimensional figure for the derivative. So of course in 2 dimension it would be very easy to imagine that. Imagine those things. So in that case, when you find at some point that the gradient of t is equal to 0, and you get and you be able to determine that point, then if you substitute these points to the function, then you will be able to get the extrema of that function, the maximum value of the function or the minimum value of that function. So to fully understand that concept, we use the concept in an example. So find the gradient of r equal to x squared plus y squared plus z squared raised to the 1/2, or square root of x squared plus y squared plus z squared. This is the generalized Pythagorean theorem. So if you get the gradient of r, the gradient of r, of course you have to get that one and this one and also that one individually. And so if you get the derivative of r with respect to x, this is just this one here. R with respect to y, this is just this one here, and r with respect to z, this is just that one. And of course, if you combine, you have common denominators here. You can cancel the 2. So you have r prime, r hat in this case, because you will get r from here, and then of course this is just equal to r. So a vector divided by its magnitude is just the unit vector parallel to that vector. This thing says that the distance from the origin, 0, increases most rapidly in the radial direction. So for example, you have this is x, y, and z, and if you have a sphere here, then you can measure r there, the vector r, and the distance from the origin increases most rapidly in the radial direction. So r hat is in the radial direction. So here, this is the radial direction, r hat. So that's for that example. And then we explore more on the operator del. So the gradient of a vector, the gradient of a function, for example, is a vector. And of course, the gradient is the vector del operating on a scalar t. For example, when you have this one, when you write it in your notebook, you have to put the vector notation. Here it's not necessary because it's written in boldface. So this is your function t, and so your del operator will just be this one here. That is the generalized derivative. By the way, please don't forget dt, which is equal to d dot dl. This is called the total derivative. But this one is called the gradient of t. dt is the total derivative of t. So you have to remember this. Del is a vector that acts upon t, not a vector that is multiplied to t. And it mimics the behavior of an ordinary vector in every way. So let's look at that. So almost anything that can be done with other vectors can also be done with the del. However, it acts upon others and not multiply. Not ordinary multiplication, but it is an operator. So here's the difference between ordinary vectors and the del operator. So you have, if you multiply a vector with a scalar, that is just commutative. But if you do this, a gradient is not equal to this one. This one is meaningless. That product here, you have this one is commutative. This one is the divergence of V. We will learn what a divergence later on. But this is not, of course, equal to this one. Although this exists, this one exists, this does not exist. This should not exist, but this one can exist, but they are not the same. This one is not the same as that one. And when we do cross product, it's also not the same when you flip the two vectors. So say for example you have this one, but here it's not the same. Although the right side of the inequality is can exist. This is also correct. This one is also correct. But they are not equal. This one is not equal to that one. This is curl of V. We will learn those things in a little while. So what is a divergence, by the way? A divergence, if you compute it mathematically, this is just this one here. So your your del operator would be just this one, and then you dot it with this function, a vector function, for example. The Vx could be an ordinary function, Vy and Vz. They are ordinary functions, and the whole thing here is called a vector function. A vector function has directions. So this is now the divergence of V. The divergence of V. Or, of course, this is so this one. So look at that. That is that quantity now is not a vector quantity. The divergence is not a vector quantity. By the way, the divergence of a scalar is meaningless, a meaningless quantity, and it does not exist. Of course, you can say that's equal to zero. Now, what is the geometrical interpretation of the divergence of V? So, it's like when you open a faucet on your um, on your kitchen, and then when the water falls on the floor of the kitchen, for example, the point where the water falls becomes a point where the divergence occur, and the water spreads out there. That's called a divergence of the vector v. For example, your v would be um, your water, for example, and then you would see that it spreads out on the floor of the kitchen here. It spreads out. And look, the divergence as it goes away from here, from this point, source point, the divergence change in magnitude. It could change from a very small magnitude going to bigger magnitude as represented by the arrow, or it could start from a large amplitude and then you can have a smaller one, a smaller amplitude as you go away from the source point. Say for example, a charge, when you are very near the charge, the electric field, which is a divergence, the electric field, electric field, the divergence of an electric field exists, by the way. So when you go away from the charge, the electric field gets smaller and smaller. So it's a different situation here where you have a small near the point source, or the source point, and then you have larger. It's just the same thing, but for electric field, as it goes away from the charge, it gets smaller. There are also other representation of divergence. So say for example you have a source, say a line of charge, a very long line of charge, then the divergence would be going in that direction. So this one is like a point charge, or it could be this one. So if you have a line source, so as an illustration, I will just read this. Imagine standing at the edge of a pond. Sprinkle some sawdust or pine needles on the surface. So if you know what a sawdust is, when you cut a piece of wood, and the dust that falls down from the saw where the wood is being cut, that's called the sawdust. And if you get the sawdust and put it in the water, it spreads out. That's divergence. That's positive divergence. But if they collect together like iron filings on a paper, and then you put a magnet there, the magnet will collect together the iron filings. That's called a negative divergence because it's collecting together. That's I mean, that just an analogy, but that's what we call negative divergence, and the spreading out is called positive divergence. So for example, a point of positive divergence is a source or faucet, and a point of negative divergence is a sink or drain. So because when you have a source, it's the water spreads out, and then when you have a sink, the water collects into the drain. So that's just the meaning of that. So example, given this vector function, and then you also have another vector function here, another vector. Calculate the divergence of these three vector functions. So say for example VA, the divergence of VA, then this is just the derivative of x with partial derivative of x with respect to AX. I mean x. Derivative of y with respect to y, and derivative of z with respect to z. So you have 1, this is just equal to 1, 1 plus 1, that's just equal to 3. And then if you get the divergence of VB with respect to I mean, you get the divergence of VB, for example, and then also you get the partial derivatives. Partial derivative of the x here, x hat, has 0 component plus 0 component of y hat plus 1 component of the z hat. So derivative of 0 is 0, derivative of 0 with respect to y is 0, derivative of 1 with respect to z is 0, because they are all constant, so 0. And for this one you have z hat, so you have here 0, 0, and this one is just equal to 1, so you have 1. So the other special product is the curl, and the definition of the curl of V is just the same as the vector product of two vectors. So you have this, but instead of having an ordinary vector, you have an operator here, and then you have V, the components of that vector there. So your curl of V is just equal to this one. So we have to note again that the curl of a vector the curl of a vector function is a vector, and of course a scalar cannot have a curl, and it does not exist. Because scalar doesn't have direction. So this is the geometrical interpretation of the curl. So you have a source point like magnetic field. The magnetic field curls a source, the wire for example. So this one here, it curls the source. And here also, this is also a kind of curl where you have one side going in this direction, the other side is going in that direction, and of course as you go away from the source, the vectors also change their magnitude. So that's the geometrical interpretation, and that's it for now, guys. See you soon.